Alright, welcome back everybody. In our next few videos we're going to be looking at material from Section 2 of Unit 2 of AP Calculus, defining the derivative of a function and using derivative notation. I figure this will probably be 2, maybe even 3 videos. A lot of information that I'm throwing out at you this lesson. We start here with a wall of text. Let's see. We looked at, in the last lesson, how to find instantaneous rate of change. One very important thing that we had to say about the instantaneous rate of change was that it is the same as the slope of the tangent line to a curve at that point. Okay? Little did you realize at the time, or maybe you did, that we were developing one of the most important concepts in all of mathematics, especially calculus, the derivative. So this instantaneous rate of change that is the same as the slope of a tangent line to a curve, that is actually our definition of what a derivative of a function is at a point. Okay? There are a bunch of ways that we can write the derivative of a function at a point. All of these are included here. F prime of a for the function, we're talking about y equals f of x at the point x of a, the value of the derivative of y equals f of x at x equals a. And a bunch of ways we can write it. F prime of x at a. So f prime of a, that's how we say this, f prime of a. Or we've got dx of f of x at x equals a. That's what this little vertical bar with the x equals a there stands for. It stands for you're evaluating the function at x equals a. This is df dx at x equals a. And this is said dy dx at x equals a. Those all represent the derivative of the function y equals f of x at the point x equals a. And we can use any of these notations to represent the derivative. We can also write any of them using any limit of a difference quotient that we might possibly have. And so I've taken all of these derivative notations and kind of matched them up with the limits of the difference quotients that we saw in the last section. And so we see we can write f prime of a using either of these two limits of the difference quotients. Same thing, we can write the derivative ddx of f of x at x equals a using either of those limits of difference quotients. Okay? So any of the notations for derivatives can be written using any of the difference quotients. In reality, we tend to gravitate towards one or two of these notations, but it's usually important for us to recognize a wide variety of ways. I tend to, when I'm finding the derivative at a point, I tend to use these two more than any others. When we're finding the derivative of a function, the notation gets a little bit less cumbersome because we're not talking about evaluating it at x equals a, and so the other notations are more commonly used when we're finding the derivative of a function than when we're finding the derivative of it at a point. Of course, like I said, we certainly can use any of those notations, and you should recognize any of them, just in case we run into them. Alright, let's go ahead. We'll find our first official derivative at a point. We're going to find f prime of 2 if f of x is equal to 3x squared minus 5x. So I'm going to find f prime of 2 by using the limit of a difference quotient, and I'm going to use the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. Now notice I put the numerical value where I'm finding the value of the derivative into my formula at that point. Okay? And now I'm going to go about the process of doing this it's a lot of algebra and limit taking like we did in the last unit. So we're going to put 2 plus h into the function everywhere where there is an x. And we're going to put 2 into the function everywhere where there is an x. We've got all of that over h. And now we've got some algebra to do. So we've got the limit as h goes to 0 of 3 times the quantity. And the quantity 2 plus h, when I expand that out, is going to be 4 plus 4h plus h squared. I'm going to leave this for a second so that I'm distributing everything out at the same time. And then inside the parentheses there, that looks like 12 minus 10, so that's going to be 2. And now we'll get rid of all of the parentheses here and expand things out. We've got 12 plus 12h plus 3h squared minus 10 minus 5h minus 2 all over h. Now we're looking at things that combine here, and this is a very important thing for us to have happen when we're taking these derivatives using the limit of a difference quotient. Notice all the numbers, when we combine those together, combine together for 0 to equal 0. And then I've got h's that are going to combine together, and till it's all said and done, this is going to turn into the limit as h approaches 0 of 3h squared plus 7h all over h. It is very important when we're finding these derivatives using the limit of a difference quotient that all the terms in the numerator end up having an h in them, at least when we're dealing with polynomial functions or anything like that. And now I'm going to continue forward to find this limit. If I tried to evaluate this by substitution, I would end up with an indeterminate 0 over 0. So I'm going to go ahead and factor the numerator. I can take an h out of every term. And now those h's cancel each other out. And so this becomes the limit as h goes to 0 of the quantity 3h plus 7. Now I can substitute 0 in there, and I end up with 7 as the value of my derivative at that point. Something very important for you to understand: when we find the value of the derivative at a point, what we're finding is a number. We ended up with 7 as a number. If we modify the formulas from the previous page a little bit and we replace the a with the variable x, we can find the derivative in general, which is going to end up resulting in a function. Okay, and since we're replacing a with x in our formulas, the second form of the difference quotient really doesn't make a whole lot of sense when we're finding the values, the derivative of a function. And so we're mostly going to use the first form of the difference quotient that you see here. Okay, but like I mentioned, there are other forms of the difference quotient that we can use to find the derivative. What I'm going to ask you to do next, I'm going to scroll down here and see if you can figure out which of these limits of difference quotients do not represent the derivative of x squared. Okay, so go ahead and take a second, pause the video, and look at these and see which of these you think do represent the derivative of x squared and which of them do not represent the derivative of x squared. All right. Alright, now that you took the time to decide which of those represent the derivative of x squared and which don't, we'll go through and reveal which ones do and which ones do not. Okay. Part A does not. Why not? Because if you remember, the limit of our difference quotient, we were always taking x plus h and putting it into the function. in some way. We've seen this form of the difference quotient. This is trying to do f of x plus h minus f of x, but it didn't put x plus h in here for x squared. It just took the x squared and added on an h. That's why that one doesn't work. This one does represent. Okay. Part C is a little trickier for you. It's not a form we've seen, but if you imagine the curve y equals x squared, what we can do is we can, if we have a point x, and we go the same distance from it in either direction over to x minus h and x plus h. If we put x plus h into the formula and put x minus h into the formula, what happens then is this becomes the limit as h goes to 0 of, and we've got x plus h squared minus x minus h squared all over x plus h minus x minus h, which actually simplifies to this. So this one does represent the derivative. D looks like very similar to part B, the only difference being that we've got the x in the denominator, which is not how our slope formula works, so this does not represent the derivative. Okay. Let's see the next one. Well, in the next one, basically that is a difference quotient using these 2 points, where the function is at x value is at x and at x minus h. This one does represent the derivative. F looks exactly like B, what's inside the limit, except in this case we're only having h approach 0 from the right-hand side. And really, in all honesty, when we thought about this, we mostly thought about h approaching 0 from the right-hand side. We always had h as a positive value. It doesn't have to be a positive value, but this does represent the derivative of the function. And then these last two do not. This, again, looks like it's trying to use the points where x is our x coordinates are x and x minus h, but instead of substituting x minus h into the function, it just subtracts the h outside. And the last one, the denominator is a problem, so that one does not. Alright, I think that's where we're going to call it quits for this video. We'll come back next time with a second video and start to find the derivatives of some functions using the limit of a difference quotient. Alright, see you then, have a great rest of your day, and I'll see you next time.